morning and good afternoon. Thank you everyone so much for joining us for our monthly webinar. Today's webinar, we will review the theory behind our flow channel designed to measure extensional viscosity. Essentially, we'll be discussing practical aspects of testing with our e-VROC viscometer, and we will also cover flow channel selection and the potential onset of secondary flows of turbulence. This webinar will be hosted by our in-house rheology expert, Dr. Stacy Elliott. Dr. Elliott obtained her extensive experience and rheological knowledge through her education at Carnegie Mellon, Princeton, as well as her experience at Alcon and DuPont. During the question and answer session as well, we'll also feature Dr. Imam, who obtained his PhD in biomedical engineering from the University of Texas at Austin. Without further ado, I'd like to introduce Dr. Elliott.
Thank you, Grace, and welcome everyone into today's webinar. As Grace said, we're going to be talking about extensional viscosity today. So our name for our extensional chip is the e-VROC. And we're going to cover, although we didn't quite present this as one of our fundamentals or back to basics, where we're going to talk about the theory behind the flow channel and then also provide some practical tips. And after we already announced that we were going to be doing this particular webinar, we decided that in the interest of time, sometimes we get some comments that our webinars can go a little long. We're going to hold off on some of the analysis type discussions until our June webinar. So we're going to have a follow-up extensional webinar in June where we discuss some more details in data analysis. And that's actually where we're going to introduce some discussions on the secondary flows and how to look for those. So I apologize if that was the main reason you tuned in today, but please tune in June and we'll finish off our extensional topic. So I wanted to start off with, just so everything that I present today has a clear context, the basic thought behind rheology and what it is. So rheology is looking at the science of deformation and flow of materials. And you can also think of it, an equivalent definition is to think of what is the stress response that comes from a particular applied deformation. And we use fluid mechanics when we deal with rheology because we need to describe two things. We need to describe what is referred to as the kinematics, which is the flow field or the deformation, and then also the dynamics, which is the term we use for the stress distribution. So when we think about the extensional viscosity, we're going to think about these two things. We're going to think about the flow field or the deformation that we're applying, and then the resulting stress that occurs. And just a quick review, you know, our instrumentation is what we refer to as applied or controlled strain rheometer or viscometer. And that's because we do control the deformation and then we're measuring the stress. However, you can have the opposite type of technique where you're controlling the stress and measuring the deformation, but they're related. So then this leads us to, these two components lead us to what we refer to as the rheology constitutive equation. And constitutive is just the language we use for relating these two components. And it's the relation between the kinematics or the flow field, the deformation, and then the dynamics or the stress. And this is what defines all the rheological properties. So there are many rheological properties, and this is what distinguishes them. So it's going to be the stress, a proportionality between stress and the deformation. So now let's get into a little more specifics. First, just specifically viscosity, because we characterize fluid materials differently than we characterize solid materials. So fluid materials are characterized with a continuous deformation. So now we think about, instead of just deformation like a strain, we're thinking of rate of deformation. And we'll elaborate more on that in a bit. So now we've narrowed it down a little bit to viscosity. So this is what, as I said, how we analyze fluids as opposed to solids. And now it's stress over rate of deformation, because now it's a continuous deformation that we're imposing, because this is the appropriate way to characterize fluid materials. So for our technology, we are able to look at different types of viscosities by changing the nature of our microfluidic flow channel. So we change the geometry of the channel. And by doing this, if you're familiar with our technology, we have our standard channel, which is a uniform channel. to measure steady shear, and then we have our extensional channel, which has this hyperbolic contraction in the center to measure our extensional type of viscosity. So as I mentioned on the onset, we're thinking of two things. We're thinking of deformation, and then we're thinking of stress. So I'm going to point out also that when we do the steady shear properties, we're introducing the steady shear deformation, and we're looking at a shear stress. But when we introduce this extensional type of deformation, we're generating a normal stress, and more specifically, a normal stress difference. And we're going to talk about that later, just so you understand what it is that we're measuring and try to contrast that to our steady shear properties. So as I kind of jumped ahead a moment ago, our approach is to change the geometry of the channel. So if we're looking at our uniform channel, that's our steady shear. And if we're looking at this hyperbolic contraction and expansion, that's for our extensional deformation and then normal stress difference generation. Okay, so let's zoom in a bit and think about this hyperbolic contraction expansion that we introduce into the center of the flow channel. And why do we do this? Why does this change the deformation from some steady shear to what we're referring to as extensional or elongational? So when we introduce this contraction, this is going to produce a velocity gradient that's parallel to the flow. So it's in the same direction as the flow field. And the reason this occurs is if you look at the volumetric flow rate, this is going to be constant throughout the flow path. And this volumetric flow rate is essentially the cross-sectional area times the linear velocity. And so as we go into this contraction or constriction, our cross-sectional area is decreasing. So that means because we have this constant volumetric flow rate, that the linear velocity must increase. Therefore, as we're moving along the direction of flow into the contraction, our linear velocity is increasing. So now we have a velocity gradient in the direction of flow. And that's what's going to define our extensional rate. And so here we have this extensional rate in the x direction, which is just this gradient in our velocity. And this is what we define as our extensional rate. And you can think of this as, you know, acting to stretch or elongate the fluid element. And we'll talk a little bit about it more later, but the specific reason that we've used a hyperbolic contraction is that this, in theory, gives us a constant elongational rate as we enter into the flow channel. So this little plot down below our diagram here is just the linear velocity and the flow direction as a function of the flow direction. So we see as we hit the entrance of the channel, we have a linear relationship. So that would be a constant extensional rate, and exit, we also have that linear relationship. So this is the nature of the deformation that comes from this constriction or contraction. Okay, so I wanted to also point out that we like to be very clear with our technology that this is not a pure extensional type of deformation, because we still have the confines of the flow channel. And this means we still have no slip boundary conditions that apply. So that means we're still shearing the fluid. There's still a steady shear being imposed on the fluid as well. So we just like to be very clear that this is a mixed flow situation. You know, if there were a way to coat the inside of the channel so that there was, you know, a no slip boundary condition, then that would transition us to something that's more pure extension, but we don't have that option at this time. And I'll sort of discuss the idea of correcting for the presence of the shear contribution in this webinar, but then it'll be next month where we actually apply that to some data and do some more detailed analysis there. Just as I said, it would be a bit too long to do that today. Okay, now that kind of starts to address the idea of the kinematics or the deformation that we're imposing. So now we need to think about how is the stress going to be different when we impose this extensional deformation in comparison to our steady shear type of experiment. So I want to remind everyone before we go into the details here, just so you remember the nature of stress, and that stress is a tensor. And I would argue that even if you think you don't understand tensors, I would make a bold statement and say that you actually do, because most everyone is familiar with a vector. So velocity or force, these are vectors. And so we know that these have a scalar magnitude and then a directionality that has to be specified. And vector is just the more common language for a first order tensor. So when we talk about stress, this is just basically taking it to the next level. So stress, which is force per unit area, is a second order tensor. And it's a second order tensor because we now have to specify two things. So unlike the vector, where we only have to specify direction of the force, we now also have to specify what surface is this force acting on. And surfaces are characterized by unit normal vectors to that surface. This is, although thinking about it in the very general sense, it's a bit confusing. It makes very much sense when you look at the mathematics. So this is why stress is a second order tensor, and it's because of these two things. It has directionality for force, and then also what is the surface that it's acting on. So that gives us potentially 9 stress components. So we generally represent this as a matrix. And if you're familiar, and so we have then also here sort of schematic, so you can kind of see what the diagonal elements look like and what the off-diagonal elements look like when it comes to the stress on a particular surface. And so normal stresses, which what we're going to be talking about today, are these diagonal elements. And so this means that the direction of the force is parallel to the unit normal vector of the surface that it's acting on. So you can see what this is what we think of when we think of compression and extension, these normal stresses, as opposed to the shear stresses, which is what we think of when we're dealing with, say, steady shear viscosity, which is what we talk about most of the time. So that's just putting what is a normal stress, because that's what this elongational deformation is going to result in, is the generation of normal stress. And it's more specifically a normal stress difference, because you need a difference in the normal stresses to actually generate a deformation. If all normal stresses are equal, this is like atmospheric pressure, and this is an isotropic normal stress and doesn't lead to deformation. So to take it a step further, we're actually going to be talking about a normal stress difference. Okay, so just to then visualize what's happening when we take this fluid element, and so these sort of little boxes and rectangles are meant to represent the fluid element as it's sort of moving into this constriction or contraction. So what happens is we are essentially simultaneously extending this fluid, and then this leads to a compression in on the other axis. So extending in the x-axis, compressing in the y-axis as this fluid element moves into the contraction. So this normal stress difference between the direction of flow and the y direction perpendicular to flow is what we refer to as the first normal stress difference. And this net difference between the tension that is occurring as it's elongated in the x direction and the compression that is occurring in the y direction, you can think of it two ways. It's either the driving force for the extensional deformation, or it's the consequence of the extensional deformation. In the case of our experiment, where we're controlling the flow rate and we're controlling the deformation, then it's the consequence of our deformation. So as we elongate, we're also then going to be compressing in the perpendicular axis. And so this gives us the normal stress difference driving this extension. So then how do we define this extensional viscosity? Remember back, stress, the proportionality between stress and deformation rate is what defines our rheological properties. So now we're going to define our parent extensional viscosity as our normal stress difference divided by our apparent extensional rate, which we already talked about as being the gradient in the velocity in the direction of flow. So this is analogous to what we would see for our steady shear viscosity, where we have shear stress versus shear rate. But now the relevant stress and deformation rate have changed for this flow geometry. And we generally use the term apparent extensional viscosity because there's some, approximations that we're doing when we do the calculation. And we'll hint at some of those as we move along. But because remember, all of these properties are calculated, they're never directly measured. Okay, so just so that we can see how are we actually going to calculate these components, the extensional rate and the normal stress, to get our extensional viscosity. And so we're going to then take a closer look at our flow channel. So I've already mentioned, the microfluidic nature of our channel, but now to remind everyone about our technology in general, it's the combination of the microfluidics with the MEMS. So we have the pressure sensors spaced along the lower or the base of the flow channel. And in this instance, we have 2 of the pressure sensors before the constriction or contraction and 2 of them afterwards. And then I've also highlighted here all of the dimensions of our channel. So how are we going to relate all of these dimensions and then also our volumetric flow rate that we're imposing on the fluid to calculate our apparent extensional rate? So just to bring back what we already looked at before when we were discussing the general idea of the hyperbolic contraction, this extensional rate is the velocity gradient parallel to flow or in the direction of flow. And remember I mentioned that we specifically choose the hyperbolic contraction to make the calculation easier. I'll just remind everyone that, that's kind of the nature of the viscometer or rheometer, is that you want to make the flow fields and geometries as simple as possible to facilitate your calculation, because all of these things are calculated. So I didn't want to put too many equations on here, but the nature of this hyperbolic constriction or contraction makes this calculation of the derivative of the velocity very easy. And so then we can easily relate this extensional flow rate, apparent extensional rate, to Q, or volumetric flow rate, which we control, and then just the dimensions of the flow channel. So this would be the length of the contraction, the channel depth H, the width in the narrowest part of the contraction, and then the width either before or after the contraction. So this is a very simple calculation once we know the dimensions of the channel and we know the volumetric flow rate that we're imposing. Another parameter that's going to come up when we start talking about the normal stress difference is what is referred to as the Henke strain. So to get strain from rate of strain, essentially, we need to do the integral over time. So this, as we pointed out earlier, this extensional rate has units of inverse seconds or inverse time. And so then to convert this extensional strain rate to strain, we just integrate this value or this property as a function of time. And again, not wanting to go too much into the math, what we find out is that this strain is maximum as it hits this throat of the constriction. And because our channel geometry is fixed, this Henke strain at its maximum value is just related to the channel width, the 2 channel width values, and gives a constant of approximately 2. Okay, so now we know how to relate the extensional rate to all of our properties that we have in the channel and our controlled flow rate. And we understand that the maximum strain that can be experienced, that the fluid can experience in our flow channel is about 2. Okay, so now the next thing we need to actually get everything to calculate our extensional viscosity is how we're going to calculate the first normal stress difference. So this again is going to come from our pressure sensors. So we're going to need to figure out how are we going to relate the pressure drop across the contraction extension to calculate this normal stress. So again, we have the flow channel here, and then above this we have pressure as a function of position along the flow channel. And just as a reference for anyone who's familiar with our uniform channel geometry and how we use that to work with steady shear properties, if this constriction were not present, we'd just have a nice, simple, linear relationship of the pressure as we move along the flow channel. But because we introduced this constriction, we now shift this to something that's not linear across all 4 sensors. So we have a larger drop in the pressure as we go across the constriction. And because there are some limitations on how we can place the pressure sensors, they can't be placed exactly at the entrance and exactly at the exit. So we have to do a little bit of an extrapolation to get the pressure drop that we really want for our calculation. So we really want the pressure drop that occurs just over this contraction expansion. And so to do that, we just basically take the drop between sensors 2 and 3 and do a small extrapolation to get the pressure drop that comes across the contraction. So that's the first thing we have to think about, is that that's what we really need to start moving towards calculation of the first normal stress difference. So we need to correct for this offset of the pressure sensors and get this specific pressure drop across the length of the contraction. So the next thing I want to point out is that, remember, we were very clear that this is a mixed flow environment. We still, because of the confines of the channel and the no slip boundary conditions, impose a shear deformation on it. So we have some extensional component contributing to the pressure, this delta P sub C pressure drop across the constriction. But then we also have a viscous or shear component contributing as well. So ideally, this normal stress difference is going to be related to the extensional part divided by this Henke strain that I just mentioned. So ideally, this is what we want to use when we're calculating the first normal stress difference. And again, I already probably have a few too many equations for people's taste, so I didn't want to go into the exact derivation of this relationship. But this relationship comes from essentially the work energy principle. So there's a net amount of work being put into the system because of the externally applied flow field. And in the case of the constriction, this is leading to a change in the kinetic energy. It's a change in the velocity as we move through the flow channel. So it's basically that type of balance that is giving us this relationship. And I think I'll include a reference when we distribute the PowerPoint slides so that you can go look. If you're very interested in how this is derived, you can get a better feel for that. But that's the general idea, is the work to kinetic energy that we get in the constriction. So to get this true relationship, then what we would have to do is subtract off this viscous or steady shear contribution to the pressure drop across the contraction. Now, this is possible for Newtonian fluids or shear rate independent viscosity or power law fluids. However, for a general non-Newtonian fluid that has a plateau shear thinning region and another plateau, you can't analytically subtract off this contribution. So in the case of a more complex fluid where you have something that's not power law, then we kind of just have to accept that we're in this pressure drop across the constriction. We kind of have to accept that we're pulling in an extra contribution to the steady shear. So just be aware of that, as you move forward with looking at your data. Okay, so now we have everything we need to calculate. We know how to calculate our extensional viscosity. We know how to calculate the extensional rate from fluid geometry, volumetric flow rate, and we know how to calculate the normal stress difference from the pressure drop and the total Henke strain that occurs in the extensional, in the contraction. So now let's just take a look at an example of some data that we have. So this is a pressure profile. So this is real data, unlike the schematic that we just looked at. So we have pressure, and we see the pressure value at each of the 4 sensors, and we see a enhanced drop as we move into the contraction. And these red dashed lines are basically how I've extrapolated to get the entry point of the flow channel and then the exit point of the flow channel to get our delta P sub C, which is given here in red. So slightly over 3,000 pascals in this case. So for this particular experiment, as I said, our Henke strain, our total strain that the fluid experiences as it goes into the contraction, is about 2, fixed by the geometry. Our experiment here, we controlled the flow rate to be slightly over 300 microliters per minute. And this gave us an apparent extensional rate of about 150 inverse seconds, and then an extensional viscosity of about 10 Pascal seconds. So in this particular instance, this was a more complicated fluid that didn't fall under the category of Newtonian or power law, so we didn't subtract off any of the shear contribution. So, that's one of the reasons why we use this language of apparent extensional viscosity, is that, it's a ranking, but it's not a true extensional viscosity. So I also wanted to point out, since we're looking at some of the data here, is that and we're not going to do this today, as I said, it would just make things too long, but I think in our next webinar we'll do this. You can actually calculate steady shear viscosity from the pressure drop prior to the constriction and the pressure drop after the constriction. So let me jump back, not to be too confusing here, but the way it's set up are the pressure sensors are set far enough upstream and downstream of the contraction that you do have a nice fully developed steady shear flow field before and after. So we can actually use that pressure drop to calculate the steady shear properties. And that can actually, if you don't have a separate way of measuring steady shear data, this can actually facilitate subtracting off the component if you can do it for a Newtonian or power law fluid. But then also, when you look at these values, it can also start giving you an indication of whether or not we have secondary flows or turbulence. So we're going to talk about this more in the next webinar next month, but I'll just hint that the presence of this constriction makes it much more probable to have secondary flows or turbulence. That nature of this convergence of the fluid makes it more likely. And so one of the things you might see when that happens is some strange things happening, close to the entrance and close to the exit, and you can start seeing a big variation in what your steady shear properties are looking like. Okay, so let's take a quick look at what some of this data looks like. And again, I'm hinting at some of the things we'll go into more detail later in our next webinar. But so what we're looking at here, we have xanthan gum solutions in just water or perhaps a buffer. And so xanthan gum, if you're not familiar with it, it's a very high molecular weight polysaccharide. Generally, molecular weights are in excess of 1 million. And what we're looking at here is, I'm just going to try to emphasize some general points about steady shear versus extensional viscosity. So we're looking at the top group of values are the extensional viscosity for our different concentrations from about 0.125 up to 0.5% weight percent of our xanthan gum. And then down below this group here is our steady shear value. So up here is extensional as a function of extensional rate, and down here is steady shear as a function of shear rate. So what we see is that the extensional viscosity is higher than the steady shear, and this is a sort of a well-known feature that fluids, the stress response to an extensional deformation is higher than the stress response to a steady shear deformation. And this is true even for Newtonian fluids, but this can be exaggerated for complex fluids, such as this high molecular weight polymer solution. And the other thing to notice is that although we see thinning or reduction in the viscosity as a function of rate, what we see in the extensional case is this, what looks like might be extensional thickening, or an increase in the extensional viscosity, where this is absent down here under the steady shear conditions. And so this is something that we're going to look at in more detail next time. And this you have to consider, although extensional thickening is certainly possible, particularly when you're dealing with these high molecular weight polymers or other complex type fluids. You also have to consider now the fact that, as I mentioned, this type of flow channel is more prone to secondary flows or turbulence, and the sort of manifestation of the secondary flows is to see an artificial enhancement in the stress response and therefore the viscosity. So next time we're going to look in more detail and try to see, is this a true thing, a true thickening, or is this something coming from, an artifact due to the secondary flows? And, also there are different driving forces for the secondary flows. There's the most common, the inertial driving force for them, but then you can also have an elastic driving force for the secondary flow formation. And we'll talk about that next time. Okay, so now I wanted to, now that we kind of have an understanding of the theory behind our flow channel and what's happening there, I wanted to talk about some practical tips. Because you do have to look at things. This type of experiment will look a little bit different than what you're familiar with, especially if you're trying to compare it to the e-VROC channel. So the first thing we want to talk about in terms of practicality is that cleaning is always very important in our microfluidics, but it's extra important when we're dealing with the extensional channel. And I've just sort of brought the images back to drive that point home. So it's always important in the uniform channel because of our small length scale dimensions, particularly the depth. But now we're introducing this, significant constriction. So you can imagine that this, if you're not very careful on your cleaning, can easily get clogged up. And then also you can have some stagnation points as well that can be hard to clean. So just some tips if you're, working with this, or think you will be working with it, in the cleaning process. It's going to be a little more beneficial, perhaps to use elevated temperatures if that helps with solubility, and then also reduction of the viscosity of the fluid that you're trying to clean out. Some increased soaking periods to get some, diffusion of the fluid into maybe some points where it's not flowing easily. Potential for reversing flow. Now at the moment, our system isn't set up to do that easily, but we can kind of rig it up to do it in a ad hoc kind of way, so that is doable. And then also for some particular samples, you may never want to dry the channel out. It may be better to have your sample introduced into an already wet channel to prevent additional deposits or film formation that might occur that would be problematic to clean out later. So cleaning is extra important when we're dealing with our extensional chip. So now the next thing I wanted to do is sort of show you what it would look like if you were doing an experiment on our e-VROC system, because things are going to look a little different than they might when you're dealing with the uniform flow channel. So what we have here, this is sort of what you'll see in real time when you're doing the experiment. So you'll see at the top left here the transient curve. So viscosity as a function of time, temperature monitoring on the right here, and then down on the left is where we'll see the pressure readings for each of the 4 sensors scattered about the base of the flow channel. And then on the right is where, if we're doing a rate or temperature sweep, data will be sort of piled up as our experiment goes along. What I wanted to focus on though are the 2 plots on the left here. So one of the things that will be consistent when you're dealing with this type of measurement, as when you're dealing with the steady shear measurement, is looking for the transient to plateau. So we need to get a well-developed steady flow, and this will be confirmed when we see the viscosity, ramp up and then reach a plateau value. We still have a little bit of noise in this experiment because our and this will make a little more sense in a minute, but our percent full scale pressure is on the low end. It's just under 7%. So we still have a little bit of noise, but we do see the increase in viscosity and then the plateauing out. So when you actually start averaging your viscosity values, you want to make sure you only average on the plateau. And if you're not seeing a plateau, then that's going to be an indication that either your experimental parameters aren't quite right, meaning you have to extend your measurement and average time, or perhaps there's something else going on in the system that's not allowing you to reach a steady state. And then on the bottom left here, we have as I said, the pressure profile. And this is as we said, looks different than for our uniform channel, because now we don't have something that's linear. And one of the signs that we have a good experiment when we're dealing with the uniform channel is that we have an R² value that's close to or equal to 1. But now we can't use an R² value here because it will never be 1. So what you want to look at here is, so this general form that we're seeing now is, looks like a good flow profile. And by that, I mean the slope visibly, and we can confirm it later when we analyze the data, the slope visibly of the 2 pressure sensors prior and after the contraction are, approximately the same, and they're not erratic, bouncing about. They're reasonable there. And then we have this larger pressure drop through the extension. So that's what one of the things you want to look for when you're doing this type of experiment. And then the last bit I want to talk about from a practical standpoint is just like when you're doing using our uniforms channel for steady shear, you want to consider which flow channel option is best for you. So we do have multiple flow channels that you can use for the e-VROC testing. In this case, our channel dimensions are fixed, so the geometry is not something that's going to vary. So this is a difference between our uniform channels and our e-VROC channels. Our uniform channels, we can get different channel depths, but for these, everything is fixed with one geometry. However, to handle a range of fluids, lower viscosity to higher viscosity, or alternatively, looking from lower rates to higher rates, we do have differences in the pressure sensors that are scattered about the base of the flow channel. And so we characterize these by a difference in the max pressure that can be experienced by any one of these sensors. So that's the designation for our lettering here. So A, B, C, and E is just increasing max pressure that these sensors can experience. So if you want to deal with, say, higher viscosity fluids, then you need to, you're going to be very limited to what pressure range you can, extensional rate range you can access for these lower pressure chips, but then more freedom when you get to the higher ones. So this then graphically kind of represents, operation range for the different chips. So what we're looking at here, and this is kind of an estimate based on some calculations that we did in-house. And so anyone who works with these or, will work with these in the future, we can send this out to you if you want to try to look at this. But what we're looking at is basically on the x-axis, we're saying if you have some estimate for your steady shear viscosity, what type of extensional rate range can you access for our 4 different possible e-VROC chips? And, one of the things you might notice, which is kind of strange and different from our, plots that kind of guide you for our standard chips, is that we have this turnover up here, because normally we would just have 2 parallel lines representing min pressure and max pressure for the chip. But now we have this odd turnover as we move down towards lower viscosity fluids. And this comes from basically, we're trying to caution people from using, in theory, we could go to higher extensional rates. So let's just look at this EB20, and think about extrapolating this upper line over here. Technically, we can operate there and we won't overpressure the chip. Nothing bad will happen. However, we're kind of warning you that when you go beyond that particular extensional rate range, now you're getting into the flow rates where you might start, seeing these secondary or flows or turbulence that might then introduce artifacts into your measurement. So that's what that turnover is coming from. And then this, baseline down here is that we have a so I'm looking at the EA20, this baseline here that extends. Now we have a minimum flow rate that we can actually control at 2 microliters per minute. So again, although we're not at the min pressure we could access, we're at the min flow rate now in this instance. So this can then kind of guide you if you know your steady shear viscosity approximately. It kind of guides you as to what different extensional rates you could get in the different chips. And a lot of times, if you want a broader extensional rate range, you might want to combine data from from multiple chips. We've done that successfully in-house. Okay, so hopefully that's kind of foundation, and for people that are new to the concept of extensional viscosity, hopefully you now kind of starting to understand what it is and how our technology handles it. And so what I want to sort of say is, next month we're going to go in a little deeper and have a part 2 to this topic, and it's going to be more related to analysis. So we'll talk, some of the things we'll talk about are, because this is a very different type of flow field, as we've mentioned, and stress generation, it will talk more about how do we calibrate these or confirm performance of the flow channel using viscosity standards. And then also, as I mentioned, it's a mixed flow, and in certain situations you can actually correct for this mixed flow environment and subtract off the steady shear contribution. So we'll do some examples of when that's possible and what that looks like, what that process looks like. And then, I hinted also when we pulled up the data for the xanthan gum that just like standard or steady shear viscosity experiments, you can have artifacts because these are calculated properties. So how can we use some different dimension? I meant to, I have a typo here. I meant to say dimensionless groups, non-dimensional groups to interpret data. So some of these would be what's defined as the pressure coefficient, the Reynolds number, which might be familiar with some people, inertia to viscous forces in the system, and then the Deborah number, which relates to relaxation times of the material compared to characteristic time scales of the fluid. And then depending on how long I think all of that will take, we might add some more into the discussion as well. That's what we have planned for next month. So what I'm going to do is pause there and take a look and see if